Learning to predict scene-level implicit 3D from post-RGBD data. Our goal is to reconstruct the 3D of the scene, including invisible surfaces. At test time, we infer on a single unseen RGB image, and at train time, we train with post-RGBD data. We use implicit functions to represent our scene. On the right is an output generated from our method D2DRDF. Our goal is related to a lot of prior work in 3D, and we show the most relevant ones here. Works like FIFO and Deep SDF train on watertight object mesh data. GIFs and NDF train a point cloud to 3D implicit field on non-watertight mesh data, which differs from our single image to 3D problem. DGS and DRDF train a single image to 3D implicit function, but use non-watertight mesh supervision. At inference, our method takes input a single RGB image and considers points that belong to the view frustum of the camera. We consider one such point as x, which projects at pi of x in the image. We extract the D features corresponding to this point pi of x and use an MLP f to predict the distance to the scene. One such distance is the unsigned distance function UDF. UDF requires a decoding strategy that finds the minimas of the distance function to recover 3D surfaces. However, our choice of distance function is a ray-based distance function. We consider ray projecting at the red dot in the image. This ray intersects 3 surfaces, 2 of which are occluded. An unsigned ray distance function for all the points on the ray measures the least distance to the intersection and requires a decoding strategy that finds points with values close to 0. Instead of URDF, we use DRDF, which is a modification over it. DRDF assigns positive minimum distance for points before the intersection and negative minimum distance for points after the intersection. DRDF's decoding strategy finds positive to negative 0 crossings at inference. Kulkarni et al. Have showed that ray distances are better than seen. They show that DRDF is well behaved under uncertainty and is easier to decode. How can we train a neural network to predict the DRDF for all rays in a single image by using post-RGBD data? On the right, we show the 3D of the scene and the camera. We now show how to use the post-depth data to supervise a DRDF for all rays originating from the reference view. Our key insight is to use auxiliary views to supervise occluded regions along rays originating from the reference view. We show the camera of A on the right. The view B can observe parts of the scene that are occluded in the reference view. The view C can observe the side of the bar counter that is not visible in the reference view. For instance, consider a ray shown by the red dot on the image. On the right, we show the same ray in 3D. We observe the same ray from another view B. Now we wish to supervise the distance function for point ZR on this particular ray. To do this, we consider the occluded segment in B, as shown with the white box. For every such occluded segment, we identify the start of the segment and endpoints on the segment by checking the Z value in the camera B and the recorded depth map. Here, the start of the segment is labeled as an occlusion event, shown in purple circle. As the ray becomes visible, it passes beyond the bar counter. We label the end of this segment as an intersection as it passes through the kitchen counter, shown in a blue square. We see the ray in 3D intersects the kitchen counter. Now for such ZRs on the segment, we wish to supervise the value of possible DRDFs by constraints for the segment. For instance, in this case, ZR belongs to free space and is delta away from the intersection. Now we show a representation of this event along the ray for the point ZR. We can do the similar process for other auxiliary views and recover different segments. For view A, we can recover an occlusion intersection segment. For view C, we can recover an occlusion segment. Now let us consider the OO segment from view C. This segment tells us that there are no intersections on this segment. Consider a point Z on this segment denoted by the black dot. For this point, let the value of DRDF be minus 0.25. This would imply that there is an intersection at 0.25 units behind Z at Z minus 0.25. This disagrees with the evidence we see in view C. Now consider another case where the DRDF at Z is minus 0.75. That means that there is an intersection at Z minus 0.75, which is beyond the occlusion event. We do not have evidence to refute this in view C, hence minus 0.75 is a permissible value. Now if we consider the value of DRDF to be minus 0.5, that means that there is an intersection at Z minus 0.5, which is right before our occlusion event. Hence, this value is a boundary of permissibility and is a limiting case of our analysis. This gives us constraints that DRDF values must be beyond the lines passing through occlusion events with slope equal to -1. We show a plot of possible DRDF values and how they violate these constraints. The values in red are the largest penalties and the one in white are zero penalties. This leads to two regions that are permissible, R1 and R2. By doing similar analysis, we can do a similar plot for the II segment. This leads to equality constraints. The OI case is a mixture of last two cases, and the DRDF values that are allowed must come either from region R1 or R2. The IO case is a symmetric version of this case. Now we have these penalties and we show how to use them to train a D2 DRDF network that can predict DRDF values for point Z. Consider the image and the auxiliary depth maps. For a ray and a point X on the ray, Z of R, we extract the pixel aligned features from the backbone and use an MLP to predict the distance function value. And finally, we use our auxiliary views to extract constraints for the segments along the ray and impose this additional loss of entropy, the details of which will appear in the paper. We visualize qualitative results on previously unseen RGB images from Matterport 3D. We show surface normal legend on the top. We use this color scheme to color only the occluded regions. We see that our model recovers a completely occluded room, the inside of a kitchen island in purple, and the wall and the floor occluded by the chairs in pink and purple. Quantitatively, D2 DRDF slightly outperforms mesh DRDF on scene F1 score and is second across the table on ray F1 scores. We additionally perform robustness experiments to show that D2 DRDF is stable when training with sparse views, additional details of which will appear in the paper. We show an ablation experiment where we adapt the D2 DRDF model to a scene from the test set. The adaptation improves the quality of 3D reconstruction. More details are in the paper. Thank you for your attention. Please check our other videos for additional qualitative results.